So we'll look at central limit theorem, but before we do a little bit of background, I've got some notes on the board, but we need some background about this. And essentially, if I wanted to find information about a population, let's say in the example I put up yesterday, the weight of bunnies in an area. Now, I can do that in a few ways. I can get every single bunny in the population, weigh them, put them on a graph, and talk about the distribution like that. What's the problem with that?
It's hard to do.
Very hard to do. So instead of doing that, what I do is I create a whole bunch of samples. So I grab, say, 5 bunnies and I weigh them. Grab another 5 bunnies and I weigh them, and for each of those, they're called my parent population. I get a distribution about their mean weight and their standard deviation. The main thing is I get their mean. Cool? So I get the mean. What's the mean? The average. I get the average of those 5 bunnies and I put them on a graph. And regardless of how the original data looks, when I get that data and distribute the means, it will form a normal distribution. So I'll just say that again. Regardless of the type of distribution of the parent population. So an example might be rolling the dice. When I roll the dice, every option is equally likely, correct? What's the likelihood of rolling a 1, 2, 3, 4, 5? What's that probability? 1 on 6. What's the mean of that? The theoretical mean? 3.5, correct? 3.5 is the theoretical mean. So if I was to roll 5 dice and collect the means over time, what I would find is that my means centre around 3.5 and they form a normal distribution, which means that I'm more likely to get a mean of 3 than I am to get a mean of 1. Does that make sense? How would I get a mean of 1 if I'm rolling 5 dice? How would I get a mean of 1 if I'm rolling 5 dice? I'd have to roll 5 ones in a row, correct? Whereas a mean of 3 is much more easy to achieve. So what we would find is a normal distribution, even though our original population looks just like that. It's a discrete random. Sweet? Equally likely. What we need to know from a point of view is that the mean of this distribution, so the mean of our new distribution, will have the same mean as our theoretical mean. So in that dice rolling scenario, if I was to put my data on the point, I'd expect my mean to be 3.5 of my normal distribution. And the standard deviation is equal to the standard deviation of the original population divided by the square root of the number of samples. So what that means is that our sample size n, as it gets bigger, our standard deviation for our daughter population or our manipulated data becomes thinner and thinner. Cool? What also we need to take into consideration is that this only works if we have a large sample size. So if we haven't got a large sample size, there's no guarantee that it will form a normal distribution. So if I roll 5 dice 3 times, I'm not guaranteed a normal distribution. How many would I need to roll to get a really accurate? So I'm rolling my dice 5 times. How many do you think you would need to get your mean at 3.5, a nice bell curve around that? How many do you reckon you need? 10? More or less? More? 20? More? 30? 100? Getting closer? Would you be certain of it? If I had made you bet your life, would you put your life on it? No, but you'd be pretty confident but not certain. How many would you need to be certain? 1,000? I'd be pretty confident at 1,000, I think. Cool. How big does the sample size need to be? Well, how long is a piece of string? It depends. But we know that it needs to be sufficiently large. So if we see, let's see a sample size of 10 or 15 or 20, we're sitting there going, that's not big enough for us. We need more than that. Be aware that a normal parent distribution will achieve normality faster than any other type. Cool? So the more normal the distribution initially, the quicker it will achieve normality when we're going through this process. So what is that process? Just remind me, because I'm getting some vague looks in the room. What's the process involved? If I'm trying to find out about a mean or about an average of a population, how could I do it? There's two ways. First way,
The number of trials times probability.
yeah, I can just grab all the population, multiply it by, or just collect their averages, add them all up and divide by that, but that's a long way to do it. The method you're talking about, we need to know what the probability is, which we need all the samples for. Or, rather than doing that, I can just collect smaller samples, lots of smaller samples, and take their means, distribute their means, and it will form a normal distribution around the theoretical mean. Cool? And that also allows us to apply, because we've got a normal distribution, why is that powerful? Why is that important? Can we do much with these distributions? Are they very powerful? What were we just dealing with normal distributions? If I tell you you've got a normal distribution, what can you do?
Look at the standard deviation.
You can look at the standard deviation. That tells you something about the significance of your events. You know how we were finding the area? So then I could say, well, what's the probability if I've got a sample of 50 people, what's the probability that their mean is above this amount? 95% I might say. I might want a confidence interval of 95%, and that's where we're heading with this. So we're heading down using this property to add confidence, mathematical confidence to decisions being made. Sweet?
Wait, so is this the same as what we were doing, except for the values are from different samples?
Yeah, so what we're going to start with, we'll ease into it, but we're going to start with various types of distributions, and you're going to transform it into a normal distribution. Cool? Using this equation, that's pretty much the only equation you need to use at the start, and a solid understanding of that. So just to talk about these here, right? Just these before we take off. The ones in blue are our parent distributions. An example of how this would look, I'll do in red. Is something like that. Around our mean for our bimodal. Much the same. The red's the distribution of the samples, means. So if we were getting 5 samples, for example, 100 times, that's how those would look.
So what's the blue then?
The blue is the original. So this might be, for example, in the one we're talking about, the wingspan of dinosaurs. They've got 2 breeds of dinosaurs here. One's got a really small wingspan, one's got a really big wingspan. So that's called a bimodal. And if we were to take the averages of that, we would find that they sit in the middle. Cool?
Okay.
And then for our normal distribution, it will follow the same pattern, but just have a smaller standard deviation. Cool? It'll be nice and tight. Happy with that? Smaller standard deviation means we have a smaller z-score, etc., etc. Cool? That's cool.